Last week we already finished with the terminology of the graph, and we learned about the path. Do you still remember what is simple path? So path such that all its vertices and edges are distinct. So we have a simple path if it is no redundant attribute here. So we have V, and then we go to B, and then via X and H, and then we go to Z. So if everything is distinct, then we call this is simple path. But a path that is not simple because we can visit one node multiple times. So for example, from U to V, so we have U, and then visit C, and then go to W, and then we go to X via E, and then we go to Y via G, and then we go to W via F. So W is visited 2 times. That's why this is a pair that is not simple. Cycle. What is the meaning by cycle? If we deal with the cycle, means it is a circular sequence of alternating vertices and edges. So its edge is preceded and followed by its end point. Its edge means this one is the edge. It is preceded and followed by its endpoint. This is the endpoint. This is the endpoint. Simple cycle is a cycle such that all its vertices and edges are distinct. Okay. Now let's see if we have C1. C1 is a simple cycle. Okay. We call this is simple cycle. So we have V, and then it is ended to something. So we call this is the circular sequence because the vertices should be the same from the origin and the destination. So if you look at the V, we have V and then go to X via B, and then it goes to Y via G, and then it goes to W via F, we go to U via C, and then we go to A, and then return back to V. So we call this is a simple cycle because no vertices and no edges which are overlap. But we can say, we can see from this C2, it is a cycle that is not simple because it goes to W via C, we go to X via E, we go to Y via G, we go to W via F. So there are 2 W's because it is not distinct, so it is a cycle that is not simple. Okay. That's the difference between simple cycle and cycle that is not simple. Now, we will have the properties. Let n be the number of vertices, and then let m be the number of edges. And then we want to see the degree V. The degree V means the degree of the vertex V. So we have this graph. So the property number 1 is the summation of the degree V will be 2 multiplied by m. So in this case, if we have this graph, okay, we have the n equals to 4. 1, 2, 3, 4. Okay. The n is number of vertices. What is m? M is the number of edges. Then can calculate 1, 2, 3, 4, 5, 6. Okay. And what is the degree of V? The degree of V, because all of V has the same edge. So it is V 1, 2, 3. So the degree of V is 3. For this vertex, we have 1, 2, 3. For this vertex, we have 1, 2, 3. And for this vertex, we have 1, 2, 3. So the degree of V is 3. And if we have this information, we can have the properties. The degree of V, the summation, will be 2 multiplied by M. It means if we have 3 for every vertex, so it means we have 3 multiplied by 4, because we have 4 vertex, then it is 12. And it will be equal to M is 6 multiplied by 2. Okay. The property number 2, it mentioned that in an undirected graph with no self-loop and no multiple edges. Okay. No self-loop means I have a node, I have a vertex, and then I can go to the node itself. This is self-loop. No multiple edges, it means no parallel edges. So if we have 2 nodes, we can have this kind of parallel edges. Okay, so this assumption, property number 2, we have no self-loop and we have no multiple edges. Then in that case, you can have this property. M is less than equal to N multiplied by N minus 1 divided by 2. Okay. So if you calculate this one, M is 6. Okay. It is less than or equal to the N, which is 4, multiplied by 4 minus 1. It is 3. Then it is 12 divided by 2. So the number of edges will be the same with this formula. This is a proof that each vertex has degree at most n minus 1. So if we have the directed graph, what is the bound? Okay, you can have the idea. If it is a directed graph, it depends on the arrow. Okay, we call directed graph because there is a direction. There is a direction. If we have the directed graph, so we can just divide by 2 for this one. So the vertices and edges are the main components of the graph. A graph is a collection of vertices and edges, and we model the abstraction as a combination of 3 data types. So we can use vertex, edge, and graph. A vertex is a lightweight object that stores an arbitrary element provided by the user. So you can define the vertex anything. Let's say in the example that we learned before, it is an airport. But you can define the vertex as a location. You can define a vertex as maybe in the traffic, it is intersection, and etc. We assume it supports a method which is element to retrieve the stored element. An X stores an associated object. So for example, a flight number. So if I have a node from Gimpo. From Gimpo to Jeju. Then I can have many X refers to the flight number. Travel distance. So I can know how big is the distance from Gimpo to Jeju. The cost. So it is related with the airline cost and etc. So we can also have another method to access what are the properties or what are the objects that we want to access. So in addition, we assume that the edge supports the following methods. So using the edge, we can know the endpoint. What is the endpoint? The endpoint means I would like to return a tuple. The tuple is u and v. So it has the vertex u as the origin and vertex v as the destination. This is for the directed graph. If it is a directed graph, then we have u and v. U will be the origin and then v will be the destination. But if it is undirected, then the orientation is arbitrary. It means, we don't care about the sequence. U first and then V next, or V first and then U next. We don't care. The opposite means if we have the opposite V, I would like to know what is the counterpart of V. So if I have this is a V and then I can connect to this other node like U be the other node. So the opposite of V is U. Or maybe we have another, the opposite of V is W. Okay, so we can select whether it is U or W. We can have another kind of ADT to check how many vertex count, how many vertices, and then how many edges, and then edges. So in this case, we have the vertex count is number of vertices. The vertices is the iteration of all vertices. And then edge count, it is the number of edges of the graph. And then the edges means it is the iteration of all the edges on the graph. We can get edge. So get edge means I want to know what is the edge from vertex U to vertex V. If it is a non-directed graph, there is no difference between get edge U comma V, get edge V comma U. For the degree V, out true. Then if it is an undirected graph, then it returns the number of edge incident to vertex V. Okay, the number of edges incident to vertex V. So I want to know if we have V, then I want to know how many vertex, how many edges out from V. For a directed graph, return the number of outgoing. So if we have the undirected graph, like this. So what is the degree of this V? We have, because out is true, then the degree of V is 2, because it is outgoing. And this one, we call it incoming. Okay, we call this is outgoing, because going out. We call this is outgoing. But this one, we call it incoming. Okay. If it is undirected graph like this one, then yeah, we do not care whether it is go out or incoming. Incident edges, V out to. So it will be the iteration of all edges incident to vertex V. In the case of directed graph, report the outgoing edges by the default. If it is the incoming edges, yeah, we can put this one as false. If we want to insert the vertex, yeah, you can insert the vertex and then x equals to none. So if we want to input the vertex as nothing, insert x, okay, it means we have the u and then v. So this is the x that we want to insert. So if you store and no element x, then it will be known, but you can save something in this x. So for example, if you want to put this one is Gimpo, then you will put the GMP as the element. Or you want to put this one as J2, then you will put the name CGU as the name. But for the X, then this will be the element in this section. Remove vertex, remove X. So you can remove the vertex, you can remove the X. So how can we define the data in the data structure? So there are two kinds of ways to design this kind of data. The first, we call it the X list structure. We call this is X list structure because we want to put the X as the list. So we have vertex object and we have X object. So the X object, this one, P, vertex object, and then this is the X object. When we call this is object, you can say that this is a class. Okay, so this is another class. So we can create a class of vertex, and then we can create a class of an X. And then in every of this class, we will have the element, and then we can have the reference to position in the vertex sequence. In the X object, we have the element, we have the origin vertex object, we have the destination of vertex object, and then we have the reference to position in the X sequence. So for example, like this, I know that the vertex based on this graph, we have U, P, W, and Z. Then I can define the vertex U, P, W, and Z. For the X, I can define E, G, F, and H. So I can define E, F, G, and H. So this is the object. Okay? This is the object, and then this is the object. And I can see that for the U, it is incident with E and G. So U is incident with E and G. For the V, it is incident with E and F. It is incident with P and F. For the W, it is incident with G, F, and H. For the W, it has incident F, G, and H. For the Z, it has only incident with H. Then we have only one. Okay. We call it vertex sequence. It is a sequence of vertex objects. For example, yeah, you can make this as a sequence, U and then V and then W and then Z. or you can make also the edge sequence. It is a sequence of edge objects. Let's say you want to start from E and then F and then G and then H. We can have another kind of list. We call it the adjacency list structure. The adjacency list structure means I want to know the adjacency of that node. So in this case, I will have only one object, which is the vertex. And then we want to check what is the incidence sequence for each vertex. Sequence of reference to edge objects of incident edges. So I know that we have the U, P, W, and Z. So I have the U, P, W, and Z. And for this U, I know that it connects to two edges, which is E and G. So you can use the way like the hash table to see this data. So we can have the chain. The augmented edge object, it is reference to associated position in incident sequences of n vertices. So let's say I have this W. So the W has the edge F, G, and H. So we have F, G, and H. If W has another node connected, let's say Y, and then let's say this element is I, then I can just have the W, F, G, and H, and then I can connect another X, which is I, and then I can put another node, which is Y, and then in this Y, we will have another list to indicate that it is incident with the SI. Okay. Because this is the adjacency list structure. The two structure that I mentioned before, it just use an object. We use the vertex object and we use the edge object. But we can also do with the matrix. So in this matrix, we call this is adjacency matrix structure, because this is the edge list structure. We are dealing with the edge and the augmented vertex objects. We have the integer key or index associated with vertex. So we use 0, 1, 2, 3 to indicate the vertex. Let's say 0 is the vertex U, 1 is the vertex V, 2 is the vertex W, and 3 is the vertex Z. So it is the integer key. And we have two-dimension array, adjacency array. You know that we, in the case of matrix, if you learn the computer programming, we have two-dimensional list. We have two-dimensional array. And we can do with this kind of graph. It is reference to as object for the adjacent vertices. So if we have a connection from U to U, then there will be something here. But if it is null or non-value, then no S. In this case, for the node U and for the node P, there is an S V. Sorry, E. Okay. So this is the E. For the node 0 and the node 2 is W, U and W, we have the S T. The old-fashioned version just has 0 for no X and 1 for X. So sometimes you can have like this one 0, sorry, this is 1, 1, 0, 0. It means if 0, we have no x. If it is 1, then we have dx. So in this case, 1, 0, 1, 0, and then 1, 1, 0, 1, 0, 0, 1, 0. Okay, so 1 means we have dx. 0 means no x. Okay. So what about the performance? It depends on how you can define the data. Now let's see, we have n vertices and we have m edges. And we assume that no parallel edges and we assume that no self loop. If you use the edge list, this is the result. If you use the adjacent list, this will be the result. And then if you use the adjacency matrix, this will be the result. Now let's look at one by one. If we use the edge list, the space that we need to use is n plus m. Why? Because when we use the at least, this is the n, the number of nodes, and this is the m, the number of edges. The adjacency list also the same, n plus m for the space. And for the adjacency matrix, we have n power of 2. Why? N is the number of nodes. How many nodes do we have? 1, 2, 3, 4. We have 4 nodes, and then we want to check for the relationship with another node. So we have this one 4 multiplied by 4. So this will be n power of 2 for the space. For the number of incident edges, the number of incident edges, if we use the edge list, so the performance will be m. Okay. Why? We want to check the incident edges of V. If we use the edge list, what is the incident edges of V? It means we need to check for every edges. For every edges. That's why the cost or the performance will be M in the worst case. What about this? If we use the adjacency list, if we want to find the incident edges of V, then we can just have the maximum is the degree of V. The degree of V means if I want to check how many edges incident to U, then I can have only 1, 2. So it is the degree of V. If I want to know how many edges incident with double, then we have 1, 2, 3. So it is the degree of V. If I want to check the adjacency matrix, then the cost to find the incident edges of V is n time. How? I want to know the incident edges of the vertex 0. Then I will check 1, 2, 3, 4. Okay. Then, it will be the same as the number of nodes. Or adjacent. So I want to know if V and W they are adjacent or not. So the edge list will have M times, but for the adjacency list, it depends on the degree of V and the degree of W. In the adjacency matrix, it's just one time. Because I know already the V and the W, so I can check whether the V and W is null or not. Just one time. Insert vertex. So if I want to insert a vertex, then it's simple, it's one. It is one. But what about the adjacency matrix? If I want to insert a vertex, then I need to make a big pause. Because whenever I want to make, if I make a new node like this one, then I need to consider another element. Okay. Then we call it at the maximum it is n power of 2. If we want to insert x, so if we want to insert x, the x list structure we just have one time. If the adjacency list we have only also one time. When we deal with the adjacency matrix, we also have one. If we want to remove the vertex, it depends on the number of edges. If for the adjacency list we have the degree of V, and the adjacency matrix we have the n power of 2. Okay, because when you remove the node, let's say this is node 4, so if you remove this one, then you will remove everything. Okay. And then when you remove the edge, it will cost only 1. This is remove only 1, and this is only 1. Okay. So which one is the best? It depends on your operation. So what operation that you do most? If you do with the insert vertex many things, this is not good. So if you already fix the vertex, then maybe the adjacency matrix is good. But if the node is expanded, or sometimes you want to remove the vertex, then maybe S list or adjacency list is better. Okay. So in the Python graph, maybe I will give you example later. In the book, they mentioned that they are using the adjacency map representation. So we can use the Python dictionary to represent the secondary incidence map IV. So the list V is replaced by a top-level dictionary that maps its vertex V to its incident map IV. Note that we can iterate through all vertices by generating the set of keys for dictionary key. The vertex does not need explicitly maintain a reference to its position D because it can be determined by one expected time. Okay, so this author mentioned that if we can use the adjacency map, then it will be one of the ideal. Okay. So this is the class that the author proposed. We can make the class vertex, and then we can determine what is the element of this vertex. And then if we construct the element, then we have the name of the element. And then if we want to know the element, we just return the element. So if we want to put it into a map, or if we want to make it as a hash table, then we need to map into one integer value. So the one integer value means I need to define what is the ID. And then after I have the vertex, I need to determine what is the edge. So we can make the class X. And then the class X, it contains of V, U, and what is the element. So we need to make three arguments or three parameters. U is the origin, V is the destination, and X is the element. It means maybe the cost. How big is the cost from Gimpo to Jeju? Or what is the distance between Gimpo and Jeju? Or what is the flight number between Gimpo and Jeju? Then everything it can be in the element. We can define the endpoints. What is the endpoint? So the endpoint means if I have a particular X, then the endpoint will be the origin and the destination. What is the opposite? So if I know this is the phi, then the opposite of phi is, we will check. It will return the self destination if phi is origin. If it is not, then returns the origin. Okay, try to understand this step. And we can get the element, and then for this X, we also can map it into a phi. So here it is how to map into the adjacency map. And we can also do with this graph. So we have the vertex V, we have the X, and then we have graph. What is graph? Here we can do the initialization, the constructor. So you can define whether it is a directed graph or not. If it is a directed graph, then you can put it as true. If it is undirected, then you can put it false. And then we have the outgoing and we have the incoming. If it is directed, so we can have the incoming and we can have the outgoing. But if it is false, then let's have only one, which is outgoing. We will check if it is a directed or not. If it is a directed, then we will have incoming is not outgoing. So we need to distinct. It means I need to distinct the node. So the incoming is not the outgoing. Okay. So that's the meaning by is directed. The vertex count, I'll just count how many outgoing. For this is, I would like to know the key. Edge count, so I want to know how many edge count. So it will be the total. If is directed, so if it is directed, so I would like to know the total. Otherwise, the total will be divided by 2. And then if I want to know the edge, so I can have a result. So the result, it can be a set. And then the result, we can check from the secondary map for the outgoing. And then I would like to update based on the secondary map value. So I want to know how many edges, and I will do iteration for every edges on the secondary map. Get edge, so I can get what is the outgoing, U get V. So this is the get edge from U is the origin and V is the destination. We can also make degree. It means I want to know what is the degree of V. So if it is outgoing through, then I will just look at the outgoing. So the adjacent, okay. I would like to see the outgoing. If the outgoing, it means if the outgoing is true. So if it is true, then I will just look at the outgoing. If it is not, then I will look at also the income. And then I would like to call the adjacent V. It is a list, and I want to know how many of them. If I call the incident edges, I have also V, and then outgoing is true. It means I am also checking. If it is true, then let's just return the outgoing. If it is not, then also return the incoming. And then you will do the adjacent V values and then yield X. You still remember this one? Yield. We want to save into the memory. And then if we want to call again, then we can look using the formula. Okay, so this is the method that you already learned in the first before the exam. And then we have the insert vertex. For the insert vertex, we will insert the vertex into new object V vertex, and then define the outgoing of V as empty. And then let's check if it is true for the directed or not. If it is true for the directed, then let's make the incoming as plain. If you want to insert the X, yeah, then you will make the object X, U, V, X, and then the outgoing will be the outgoing U, V, and then the incoming V, U. We need to define this one first, just in case if the graph is a directed graph. Okay. So actually this code, yeah, you can develop by yourself. Okay. At least we have those kind of elements in your graph, and yeah, you can apply the graph in your problem, maybe in your project. Okay, I will finish this one. Any questions? Okay, then we will meet again on Wednesday. Thank you very much and have a good day.